Okay, seems like we're live and our attendees are with us. So are the panelists. Welcome everybody to our last panel of the 2020 edition of Next Generation Electrochemistry, also known as NGenE. This is a 1 week workshop that we've been running. This is the 5th year that we run this workshop. And normally it's run face-to-face and again for a week. Where we have lectures. This year, the COVID-19 pandemic prevented us from being able to do the face-to-face version, which would have been held about 3 weeks ago. But instead, we decided to move into a condensed, very concentrated online program with panel discussions to keep them a little more interactive than a lecture would be when you go online. NGenE is funded by NSF. They've been supporting us since 2016 very generously. The Electrochemical Society sponsors us, and they've been helping us a lot with diffusion of the event. Some of you may have received notices from ECS that this was happening, also on their Twitter feed. And it's administered by the University of Illinois Chicago. My name is Jordi Cabana, and I'm in the Department of Chemistry at UIC. And I'm the director of the program, and I've been the director since the creation 5 years ago. Thomas Allan, who's also in this webinar, is our chief administrator, meaning that if he wasn't there, none of these would happen. And also we have George Crabtree, our supporting director, who's also at UIC and Argonne National Lab. So this is our 4th panel and the last one, but not the least. This is how we've run NGenE 2020. It's been different from other editions. We've done 4 90-minute panels between yesterday and today. And the one that we're holding now is on the topic of organic electrochemistry. If you see, each of them has covered different topics and even different aspects of how to do electrochemistry, for example, yesterday afternoon. The way that the panel runs is it's meant to be a very informal or a spontaneous discussion among the panelists. These are eminences in the field, and I'm not saying this just because they're listening to me. This is, you can just check the record and you'll see for yourselves. These are experts in the topic at hand, and we want to hear their perspective on where they think that topic is going in terms of research. So first, they will give a 5-minute opening statement. The goal there is to lay out, for them to lay out the key fundamental questions, in this case, on the topic of organic electrochemistry, and to try to connect it more broadly to how to advance electrochemical science. After that, those short opening statements, that's where the discussion starts. The discussion is still driven by the panelists. But we also have a selected group of around 40 students and postdocs that are in this Zoom call. And they are given the opportunity to participate in the discussion as well. NGenE is a student-centered program, and so we want the attendees to be very interactive and not shy. The event is live streamed through YouTube. This is the 4th panel, the 3rd live stream. It seems like we solved the issue with the first live stream yesterday. And we had an initial sign up of hundreds of people that were interested in the event. So hopefully there's just as many listening to us. So we have 90 minutes. Zoom nominally doesn't kick us out after 90 minutes, but so in this webinars before, we've gone a little over, but we won't, we'll either stop right at 90 minutes, especially if our panelists have other places to be, but we won't go very much over 90 minutes anyway. For the panelists, or we refer to our panelists as our NGenE faculty. Some of you are new to the program, so just an emphasis on spending time talking about where we need to go with research in this particular area of electrochemistry, and don't be shy about showing the deficiencies in the field and where our knowledge ends and our lack of knowledge start, where that frontier is. We've had some level of controversy kind of going back and forth, very collegiate, very playful at times. Controversy, in my opinion, is good. as long as it's collegiate. So don't be shy about saying things that you think our colleagues are not going to agree with. That's the purpose of the discussion. You're reaching an audience that goes well beyond your groups. And these recordings are also going to be shared with the ECS YouTube website. So people are going to watch this after the event is done. So this is your opportunity to have your ideas pervade in the field beyond the training that you're giving to your students. Share how you think critically and how you try to keep the basic issues of electrochemistry at hand when you're doing your research. For the students, you've seen this before, so I'm going to go through this very quickly again. Please get involved. Please ask questions. I know that in some cases I can't get to all the questions, but I'll try to get as many in as I can. Your mics are disabled, a reminder. You'll get brought in once you have a question that seems to be going in the direction of the discussion. And I'll allow you to participate and give you the floor so that you can ask. Just in case, put the question on the chat. In case you have an issue on your end, we can still ask the question and I can read it. Don't be afraid to ask difficult questions. Don't be afraid to challenge what the faculty are saying. This is the whole point of this event. And then see how this falls into your career and how it connects to things that you're doing. There was questions this morning in the water treatment from people that are working on water electrolysis for energy, and they saw a connection, so that's great. With that, I'm going to stop sharing my screen. And we agreed that the first person to go would be Kevin Muller, who is at Washington University, St. Louis. We also have Song Lin from Cornell University, Phil Baran from Scripps, and Shelley Minteer from Utah. And we're going to go in reverse alphabetical order. Kevin, the floor is yours.
All right, well, thank you, Jordi. I really didn't plan anything too fancy. I just wanted to give an introduction and with an emphasis on a perspective. And what I put on my first slide is just the common view of organic electrochemistry and what it has for synthesis. And this common view today is that it's a really nice way to recycle all kinds of, recycle all kinds of catalysts or oxidants. The ones that are on the slide there, the 6 of them are all oxidants that we have recycled using sunlight as an energy source to drive an electrochemical reaction. And the idea is that you can recycle toxic or expensive chemical oxidants and you channel the redox waste product to something more benign. And this is really common for the oxidation side of things because, well, it's a stoichiometric oxidation, it's going to need a stoichiometric reductant. And so what you do is you channel that towards the reduction of protons to form hydrogen gas. But what I want to point out today and just help push the conversation towards is a broader picture than that. If we just focus on sustainability in organic electrochemistry and what it has to offer, we really miss a lot of what it can contribute. Organic electrochemistry is a unique environment for the synthetic community. It does things in different ways, and that means unique opportunities for all kinds of selectivity. And it falls into really 2 categories. There are direct electrochemical reactions where we make reactive intermediates directly at an electrode surface and follow them. And there are mediated or indirect electrochemical reactions where we use chemical oxidants or reductants to mediate a reaction for us. And they do different things. But many of the features of electrochemistry are common. And if I'm just going to focus initially on the direct electrochemical reactions, I want to point out that you can make highly reactive intermediates, radicals, radical ions. We work with radical cations a lot that operate on the picosecond time scale in terms of their half-lives. And so you can make really highly reactive intermediates. And you make those under neutral conditions. And neutral conditions is a little bit of a misnomer. For an electrolysis reaction, the pH will stay at whatever you set it at. And so it's really kind of an interesting way to make a highly reactive intermediate under this controlled set of conditions. We have control of potential. We can either adjust it or let it float so that you can, well, maintain a constant pH, but let the oxidation potential vary. I tell you the most interesting example I saw of this, and it was one of the ones that got us interested in electrochemistry years ago, was when I was a graduate school student. Larry Miller published a coupling between two aryl rings, two electron-rich aryl rings, in the presence of a tertiary amine. He did it by controlling the pH so that the amine would be protonated. And this ability to adjust the oxidation potential while leaving the pH exactly where we set it was just fantastic. And it gave a new opportunity to do a coupling reaction that, you know, I certainly hadn't seen before, didn't think of it as being possible. We also have other things in electrolysis reaction. There are double layers that protect the reactive intermediates from trapping, very common in things like the adiponitrile process, where you protect the radical anion from trapping with water. All of these things combine to let us take a look at these reactive intermediates and vary, well, structural features of the reactive intermediate that may change its oxidation potential, but we can still study it under the exact same reaction conditions. And that gives us the ability to do structure-activity relationships that lay a foundation for understanding how the intermediates behave and designing synthetic reactions. And that's a power that we have using electrochemistry that we simply really don't have using a normal chemical reagent. The same things happen in mediated electrochemical reactions. You generate reactive catalysts. You can populate multiple oxidation states in that catalyst. It's a beautiful work by a number of groups. There are neutral reaction conditions, again, control of potential. Again, you can do structure-activity relationships on catalyst development, something that we do on microelectrode arrays nicely. And you can manipulate multiple catalysts in the same reaction flask at times. And these are all really neat opportunities. So as we move forward, I think our role in terms of the electrochemistry community and opening electrochemistry up for the synthesis community, there's too many words and I'm not going to read it. But the real role that we have is that, well, there are all these interesting, strange things for the chemistry community. There are electrolytes, there are electrode surfaces, there are current, for constant current versus constant potential. And we can look at those as challenges to adopting electrochemistry, and certainly they are at times. And we can answer questions about that. But really what we want to start recognizing is that all these unique features of an electrolysis reaction give us a unique opportunity to control a synthetic reaction in ways that, well, you might not have possible in any other way. Just as an example, the electrode surface, if it really is being involved in a reaction, can be used to control that reaction and give unique stereochemistries. How do we actually tune that electrode surface to get selectivity in a reaction that we couldn't get in any other way? So in short, my message to people who are thinking about electrochemistry and its interplay with synthesis is that for much of the past 4 decades or so, our community, the kind of the organic electrochemistry community, has been working to illustrate how to take advantage of electrochemical reactions and to teach the community, the larger synthetic community, how do we think about these reactions. I think as we move forward, our goal is to really start looking at all the opportunities electrochemistry has to offer in terms of controlling a reaction and its selectivity, and then to, well, help the community and ourselves take full advantage of everything electrochemistry has to offer, from the use of electrolytes to control a reaction to efforts on an electrode surface. And with that, I'm going to stop. I think I may have kept it under 5 minutes, maybe not. And I will leave it on to the next person. So let me stop sharing my screen here.
Thank you, Kevin. You know, I said 5, but there's flexibility, okay? Don't worry. Okay, Shelley, want to give it a go?
Yes. Okay. Hold on just a second. Okay, can everyone see that now?
Yep.
Yes, okay. So from my perspective, I kind of want to start by reiterating something that was actually said by Claire and Tito yesterday morning, that sometimes it's not about the individual chemistry that you do. So there was a postdoc, I think, who asked the question of sort of which chemistry should you choose to start your academic career. And they said it's not about the chemistry is going to change your career. It's about the techniques and methods that you're using. And I think within organic electrochemistry, that's definitely the case. It's absolutely the case. So you may have individual interests, and these are kind of the 3 interests in my group. So kind of looking at extreme potential, whether that's extreme reductive potentials or extreme oxidative potentials, and looking at making electrocatalysts as selective as possible. But I would say that, you know, I'm agnostic to the actual chemistry that we're doing. So I don't really care whether it's a heterogeneous catalyst that we're going to make selective or a molecular catalyst or a biological catalyst. I care more about the sort of materials and techniques that we're going to use, the sort of methods and techniques that we're going to use to be able to address those chemistry questions from a fundamental chemistry perspective. And so if you actually look at kind of, the chemistry that's happening, we're trying to, kind of push the envelope, and whether that's pushing the envelope in selectivity or pushing the envelope in terms of making electrodes that are stable at extreme potentials, these questions are actually the same questions that happen in many other places of electrochemistry. So if you think about making electrode materials stable at really highly oxidative or highly reductive potentials, those are some of the same questions that people are thinking about when they're thinking about building battery electrodes that can produce sort of high potential batteries. Selective electrocatalysis in some ways is the same questions that people are asking in the fuel cell industry or the electrolyzer industry of how to make those electrocatalysts selective. And so I'm not going to really talk about specific chemistries in terms of areas of interest in organic electrochemistry, but more sort of thinking about the fact that these themes that exist, whether you're a battery electrochemist or a fuel cell electrochemist or an electrolyzer electrochemist, even you're a sensor electrochemist, apply to organic electrochemistry as well. And so from my perspective, I think the direction that organic electrochemistry is going and needs to go in the coming years is really to become more interdisciplinary rather than focusing just on the chemical reactions that we're trying to catalyze, but instead actually sort of fundamentally understanding the electrochemical interface and how we can tailor that electrochemical interface. And so that means, you've heard people talk a lot about in situ and operando techniques that people may be using for batteries or using for fuel cells. We need those same techniques in organic electrochemistry to be able to sort of look at that interface. We need those same computational techniques. So you had yesterday afternoon a discussion from kind of more the theory and computational side of those. We need sort of those fundamental questions answered because the chemistry that we're doing, but we actually fundamentally have to understand that interface so that we can tailor that interface to do the chemistry as selectively as we would like to do it. So that means that I think, all those questions that you heard about for the last day and a half, all those techniques in terms of looking at the interface in real time, doing surface characterization, coming up with a better electroanalytical techniques. In my opinion, those are as important to organic electrochemistry as they are to all of the other applications that you heard about over the last day or so. So I think for all intents and purposes, we have a tendency to think of ourselves as a fuel cell electrochemist or as a person who's really interested in water splitting or as a person who's interested in lithium-ion batteries. And really, if you think about who you are as an electrochemist, electrochemists are really, it's all about the interface. And so all those sort of same concerns, those same questions exist within organic electrochemistry. So we have much the same problems, much the same materials problems, interfacial problems that we need to work on. So with that, I will turn it over to Song.
All right, thank you, Shelley. Go ahead, Song.
All right, figure this out. Cool. All right, thanks, Jordy and Thomas, for organizing this. I'll make this very, very brief, so we have more time for discussions. I guess since I'm the least established among all the panelists, I'll talk a little bit about our research. And so we work at the interface between electrochemistry and organic synthesis, and the approach we're taking is to sort of really combine electrochemistry and homogeneous small molecule catalysis and harness their unique features and use sort of this approach of electrocatalysis as a new avenue for reaction discovery and for synthesizing, new functional molecules. So we do have, these are some of the projects we've been able to complete in the past several years. So we started by doing some electrochemical alkene functionalization reactions by means of, electrochemically generated radical species. And we also have been able to achieve sort of an enantioselective selective electrocatalysis by designing new chiral ligands. So recently, we've also sort of ventured into electroreductive chemistry. We're taking a couple different approaches, either by using the intrinsic feature of electrochemistry that can enable, essentially, you can dial in any potential you want, and then achieve the activation of highly strong chemical bonds by applying highly biased potentials. And the other approach would be to combine electrochemistry with photochemistry by doing electrochemical activation followed by photochemical excitation to access catalytic species that have very highly negative potentials. We also had some collaboration with the polymer chemists in our department and have been able to achieve the electrochemically controlled polymer synthesis. And we also have some other projects that are not electrochemistry, but these are also sort of redox catalysis where we actually use electrochemistry as a tool, such as cyclophotometry, to understand the reaction mechanism of these sort of metal catalysis systems. Now, in terms of some of the, or I guess my take on the current and future research areas in synthetic organic electrochemistry, I think these are some of the important areas I would sort of talk about. The first one is the new reaction discovery, new reaction strategy, and transformation discovery. And we know electrochemistry has been around for a long time. I think Kevin is one of the sort of pillars that have been working on electrochemistry for the past several decades. And in the past about 4 to 5 years or so, we also see the sort of renewal of interest on electrochemistry from the organic chemistry community. And much of these sort of research in the past 4 or 5 years is sort of focused on new reaction discovery. I think it's always going to be sort of the front and center of synthetic electrochemistry research, because you could argue some of these other categories I'll talk about, technology development or mechanistic studies, are sort of tailored toward, or these developments are to help new reaction discovery, to figure out, to troubleshoot and figure out issues in reaction chemistry. And so, being able to, I think in the next few years, being able to harness electrochemistry unique capabilities, this ability of temporally and spatially controlling the potential input to discover new transformations, I think it's going to be a very interesting and continue to be exciting direction. So second direction, as I mentioned, is to once we have the reactions in hand, how can we develop a new technology such as high throughput screening systems, as well as people have been using flow systems to be able to use these electrochemical transformations on large scales. And this is going to really help us to sort of more broadly apply electrochemistry in many different sectors of synthetic chemistry in both industry and academia. Now, moving on to the third thing I want to discuss, this is sort of the application of electroanalytical tools to study reaction mechanism. I think Shelley mentioned this briefly. This is sort of, some of the, voltammetry and other electroanalytical tools is sort of the bread and butter for electrochemists in the energy sector. And however, in my opinion, I think it's still largely underexplored in organic synthesis. So I think being able to learn and apply these technologies or techniques to study reaction mechanism, help us troubleshoot and discover new transformations is another exciting and interesting direction. And lastly, is to sort of integrate electrochemistry, synthetic electrochemistry with biology and materials chemistry. There's already some research in this area. I'm not talking about, I think there's a lot of research in, bioelectrochemical sensors or electropolymerization for battery research. But I'm more sort of talking about using the synthetic electrochemical reactions that people develop to try and, either study biological systems by doing, bioconjugation or making new polymer materials, or, doing biocatalysis, things like that. So this is the sort of the area that I'm least familiar with, but I think it's definitely something I think some of the panelists here actually have more experience with, but I think something exciting to discuss. And I think at the center of these all different research areas is collaboration. As Shelley mentioned, I think to be able to actually harness all the techniques available to organic chemists or to electroorganic chemists, we need more broader sort of a communication between different areas, as well as a broader collaboration. I think that's all I have. Thanks.
All right, thank you, Song. And let's get the last opening statement. Phil, take it on.
I can be rather brief because my colleagues here did a pretty awesome job, I think, of covering all the key points I wanted to talk about. I'll take it back to kind of when we started about 7 years in this area, 7 years ago in this area, and we were kind of struck in a total synthesis project with electrochemistry being the only way we could actually finish a particular molecule, and sort of went back and wondered why is it that there's this bifurcation between a large audience of people that look at electrochemistry in the area of analytical science, battery chemistry, and of course in the industrial era and making really, really large quantities of things like adiponitrile and chlorine, aluminum. A lot of people interested in electrochemistry, but in the sort of middle space here, which represents the largest body of practicing organic chemists, pretty much at least, 5 or 6 years ago, if I went to a conference and asked anyone who did electrochemistry or was interested in it, no one would raise their hand. Nobody really knew why they would need to look at it. So I think, that was where we really started and realized maybe there's some interesting untapped potential to be looked at. And so fast forward now, a few years later, we've written a review on this topic, published in Joule, and this is a figure from it. And we're sort of realizing this difference in mentality between the folks who do these reactions on really, really large scale and the folks who work in basic organic chemistry is that when you're making really small commodity chemicals, it's more of an engineering problem, and you're looking at things like the cost of an electron. And when you're trying to appeal to, let's say, a medicinal chemist at your average pharma company, the cost of an electron obviously is irrelevant, and you can even use superstoichiometric amounts of electrons. That's okay too. What they're really interested in is how do they get somewhere where they couldn't get there otherwise. Even more so than sustainability, as Kevin mentioned. I mean, sustainability is nice, and most medicinal chemists love the environment and they'll hug trees, but if you give them an option of using chromium to get their compound in one step versus learning how to set up a device to do electrochemically that'll take them a week, despite their love for trees, they love their job more, and so you're going to see a move towards whatever gets the job done. So how do you make electrochemistry mainstream? Is really boils down to finding transformations that that community will find to be super interesting and will sort of get them into a space that they're interested to entertain that possibility. So we started off a few years ago and realized the biggest problem is you've got to somehow get equipment to these people because they're not going to build their own device. And so we worked that out with a company called ICA. And so equipment is not a problem for people at the discovery level. And so, what is the sort of future areas that are of interest in electrochemistry for synthesis? I think there's an interesting, site where these two areas of the field can intersect and develop new science. So you've got the hardcore electrochemists, the people who are members of the ECS, and folks like Shelley who've been working on the hardcore aspects of electrodes and electrochemistry for years. And then you've got the synthetic organic chemists who really are more agnostic. They don't really care what the approach is going to be, but their question is always the same: how do I get new selectivity and new reactivity? And so I think when those two fields sort of come together and ask this question, that's where some magic can happen. So we've been lucky to be, Song and Kevin and Shelley and I have been lucky to be funded by the NSF to bring this question to bear in an actionable way. So the Center for Synthetic Organic Electrochemistry was recently funded, and it will answer this question of how, collaborations with the deep electrochemists can, really unearth the new reactivity possibilities. And we've actually we've done some tiptoeing in that area. We've had great collaborative publications already with Shelley and her team that show that this approach actually can work. So what are the new sort of directions that could be looked at? I think functionalized electrodes are an interesting direction because it's rather foreign to a basic organic chemist as to what happens when you functionalize an electrode and what happens to the reactivity. We have a large program in the lab working on the synthesis of new mediators or electrocatalysts that are modular in nature. There really aren't a lot of electrocatalysts that are out there that are easily functionalized and modular to look at the entire region of oxidation space to bring the heterogeneous nature of electrochemistry into a more homogeneous environment. So we're really excited about the possibilities of very simple electrocatalysts that can be brought to bear and made in a library format to elicit interesting new reactivity. And then finally, embracing the nature of electrochemistry, which is sort of understanding the heterogeneous reactivity when you don't have a mediator. What can be done there? What can be learned about the bilayer and how it is affected based on the electrode properties. So as Kevin mentioned, there's new properties that were variables that synthetic organic chemists don't really consider it in the normal flasks that they have to start learning about. That's also a great opportunity. And we published an interesting accounts that's kind of for the students or whoever's listening who is sort of new to the guide, to the area of electrochemistry, a sort of survival guide, sort of scout's manual to enter electrochemistry within 5 minutes. If you know nothing, you can download that paper, and pretty much after 5 minutes of looking at the figures, you'll know enough to get started in a lab. So that was a big question that I wanted to end with, and I'll leave it open to discussion.
All right. Thank you, everybody. It's interesting. I want to start by making a connection between this panel and the panel in the morning, because I heard you all talk a lot about selectivity, and I've always, as a chemist, I've always viewed the organic chemists. I'm an organic chemist. So I've always viewed the organic chemist with envy, because I've always thought that they can put whatever they want wherever they want it, right? And this morning there was a very pessimistic view on the ability to do organic oxidations of relevance to cleaning water that were selective. The selectivity was a big issue in terms of the challenges that were identified. In your perspective, in terms of where organic electrochemistry is broadly, in your view, how does the selectivity, is it a problem in organic electrochemistry broadly, or is it just as good as what you could do, with a conventional organic approach? Is this?
Well, maybe
I'm just wondering if they see a problem where there's.
Sorry, Jordy, you dropped off there. Am I the only one who can't hear Jordy?
Necessarily none, right?
Okay, I can hear you now.
Go ahead. Yeah, my internet connection gets a little glitchy. So
okay, yeah, maybe I'll just briefly say something before the others jump in. I think Kevin and Song and Shelley answered this pretty well. I mean, the ability to control the driving force and the rate through modulating the potential and the current is a sort of great opportunity for electrochemistry, and that's why we got into it. I mean, 7 years ago, we needed to make a natural product through an anodic oxidation, and it's the only reason we did it is because 1,000 different chemical oxidants failed, and by dialing in the exact oxidation potential, we were able to, make a particular natural product, and that has turned out to be, I think one of the main advantages is selectivity, as Kevin mentioned. So yeah, I'll let them opine now.
Yeah, I'll jump in. I view it as having two types of selectivity. A direct electrolysis selects based on potential and can be highly selective in terms of, well, we've done oxidations on the 50 millivolt level in terms of selecting between different functional groups. And it can be very helpful to do that. You can get selectivity, though, in other ways if you have a surface that a molecule sits down on. And I recently refereed a paper, which I can't comment on, but it was because it's not published yet, but it has a really beautiful selectivity where it's adding things trans to an olefin. Even when you have a diol that would normally add cis under an oxidant condition, it adds trans, and the electrode surface is involved in that, and it gives a really unique type of selectivity. There are also selectivities in mediated reactions. And a lot of the times, if you want to do selectivity in a chemical reaction that is not based on potential, you can use a mediator. And one of my favorite examples of that is all the way back to Hans Schaefer in the late 1970s, where he selectively oxidized the primary alcohol of a sugar by turning tempo over. And so thinking about the chemistry that's involved and thinking about what gives rise to mechanism, understanding, as Shelley was saying and Song hinted at the actual surface that's involved and what's going on that surface, can really guide us to think about the selectivities that we're used to taking advantage of, but I think really new opportunities in the future to get really highly selective reactions and things that we can't do otherwise.
But I would point out that our system is a little bit different than wastewater, in that usually we're putting pure or nearly pure reactants in. And so we actually typically know what's in the beaker, so to speak. And I think it's, you know, far more challenging for people who are thinking about wastewater remediation and doing selective chemistry there, because you don't necessarily know what is in, well, you may have some idea, but you don't know all of the different components that are in wastewater and how they're going to interact with your electrode or your electrocatalyst or your mediation scheme. So I think, you know, we do have a little bit of the advantage from the organic chemistry side of things, is that we are kind of controlling the inputs in a way that that you might not see from sort of the water purification side of things.
Just speaking on that very quickly, because Kevin alluded to the ability to functionalize a surface so that you can select what molecule is actually doing the reaction. Is that, you know, if you have two molecules that look similar to each other, I mean, how refined can that get? Or is that perhaps an opportunity to get creative? Because that would be a way to get out of the problem of having more than one, you know, product stream, right?
Yeah, I'll answer that very quickly and tell you that we can select between two benzyl alcohols based on a single methyl group right now. And so we're only getting 4-to-1 selectivity in that case, but it's still a selectivity where the surface is differentiating between them. And so I think the future, you know, I'm hearing exactly what Shelley's saying. I think this is a really important problem. And I think that analytical chemistry and analytical electrochemistry, which does give us the ability to select things out of a mixture based on surface recognition, I think that there are ways to turn that into a preparative process. And, you know, we're working on that. And I think that it's really an exciting area for us. And so we're actually right now working with somebody to help pull groups out of lignin mixtures, for example. So.
Is there a key, go ahead, Sam.
Oh, and I think the other panelists answered your question really well, but I'll just briefly mention that electrochemistry, you know, you say you envy organic chemists for being able to, you know, introduce anything or make anything we want. I mean, I think that element is still there, right? Because we're still doing organic chemistry, but electrochemistry does add a new dimension. I think, you know, I'll just give you an example we did in the past. Well, the projects we're working on right now is to do, you know, in situ selective catalysis. And it turns out that if we use electrochemistry versus using a chemical oxidant, you would think the reaction should go through the same mechanism, but it turns out electrochemistry actually gives much higher in-situ selectivity, because it actually allows for the generation of the reactive intermediate very cleanly without using a chemical oxidant. And with the chemical oxidant, you actually get over-oxidation and other side pathways that decreases the selectivity. And also, we also find out that actually by tuning the electrolyte, you would think the electrolyte would be innocent in the reaction, but turns out with different electrolyte, we can actually see drastically different in-situ selectivity as well, which is, you know, we think is actually because of the double layer effect, right? So if you have certain electrolytes, your double layer where the reaction happens is going to be much less polar than with other electrolytes. And that's another dimension to sort of tune reaction to selectivity. So I think these are the sort of extra layers of opportunities that electrochemistry can provide.
So with that, just as a follow-up, would that be kind of, you're selecting electrostatically by changing the electrolyte instead of selecting through molecular recognition by attaching something to your surface? Is that?
It's not the same as what Kevin mentioned, modifying the electrodes. Rather, you know, when you do in-situ selective catalysis, the reaction transition states have to be stabilized in a certain way, right, electrostatically. And so if you have a more polar reaction medium, the reaction is going to be lower E because it's poorly stabilized, or it stabilizes the wrong pathway. So that's basically it's by tuning the polarity next to electric surface that you can get different selectivity.
How well understood is that in your opinion? How well understood are those mechanisms? Because you've all talked about reaction mechanisms broadly, but you know, what's your perspective on arrow pushing, right? You know, getting to the point where you can draw the whole especially if it's a catalytic pathway, you guys are really good at doing that. So is that something that can be done easily with when you're using an electrode?
Well, I think one of the, like I always thought that the key to getting people into electrochemistry that are from an organic background, it really is a few basic things. One is perception and education. Another one is having the equipment readily available. And the third is a driving force, a forcing function that makes people want to actually do it. And you're referring to the first thing, which is just perception and education. And so, yes, arrow pushing is actually so simple with electrochemistry that it should be taught in every undergraduate class, because you can teach people about oxidation and reduction, and that's really arrow pushing, where electrons come from, where they go to. Now, the mechanistic intricacies that we're kind of alluding to in our three talks there are relating to things like, how does one understand the lifetime of an intermediate radical that's made at an anode? You know, how fast does it diffuse into solution before it reaches another partner? How do electrocatalysts work? How do you see, you know, remarkable observations like Song has published, where you can make a reaction better through electrochemistry? Those kind of mechanistic intricacies are not, I think, you know, super well understood, but that's the exciting part of it. I mean, if you understood everything about electrochemical mechanisms and they were just perfectly understood, electrode surfaces, everybody knew how to predict it. Mediators and electrocatalysts, it was completely understood, like a palladium redox cycle. I don't think there'd be much excitement to work in it, because it would just be like I don't know, like an engineering tool, like, you know, a faster stirring plate, essentially. So that's part of the excitement, is that there's still some basic science that's not understood on the hardcore intricacies of it.
But the fundamental principles are things that people can get started with really nicely. And so I'm thinking about, you know, Song talking about the double layer, and you asked if it was electrostatic, and what came to mind is a beautiful Diels-Alder reaction done by Kazuhiro Chiba and his co-workers years ago, where he actually made basically a quinone intermediate and wanted to have it undergo reactions with hydrophobic dienes and not trap alcohols in water. And so he made a hydrophobic double layer and then did the reactions in water, knowing that the double layer would be populated by his trapping group, and so that he could, at the anode, generate the quinone and have it trap things that were already in a double layer. And it's just a matter of understanding like dissolves like. It's a fundamental chemical principle. And so I think that helps drive things. I think we lost Jordy, huh?
Yeah, he said Zoom just kicked him out.
Okay.
I do think, you know, his question was kind of, you know, how much do we really understand these mechanisms? And I think, you know, that goes to us kind of, you know, obviously, as Song said, using good electroanalytical tools. But I think in the future, that's also us going into sort of next generation techniques. So if you look at the operando and in situ people who have, you know, been looking at catalysts with IR and with Raman, a lot of those techniques haven't really been applied to organic electrochemistry yet, and they're going to be very useful tools for us in sort of validation of mechanisms as we go forward. So I think there's a lot of future there that is really kind of a bit untapped.
I would agree with that fully, because what Phil was saying about it being a matter of controlling rates of very reactive intermediates at electrode surfaces will help us, because we need to have an idea of what the rate is and how do we control the relative pathways. So probing that, monitoring that's great.
Hey everybody, it looks like we actually, so this is Thomas. I'll cover for Jordy as he tries to find his way back in. But it looks like we have a question from Michael Gerhardt, who has been one of our champions in the previous 3 panels as well. Hey Michael, I'm gonna go ahead and allow you to talk. Why don't you ask your question?
Sure. So I mean, I have a teaching question that I've asked everyone that I can save till the end, but one of my kind of more research questions was, how generalizable are results when you're talking about selectivity for certain molecules in certain reactions? Like if Phil discovers, for example, that he can make some molecule with 90% selectivity, under what conditions or in what cases could one of the other panelists then use his result to enhance the selectivity of creating a different molecule?
that's a pretty broad question. I think that it's a good one. It could be asked of any organic transformation, honestly. And so I think that the way that the people in the center have tried to approach organic methodology, and our lab's approach to methodology in general, is to have as large of a substrate scope as you possibly can that demonstrates limitations and shows selectivity and sensitivity to a broad array of functional groups. Because I think that question could be asked for any reaction in organic chemistry.
And I think one of the challenges that we have is, you know, across the group is a plethora of different catalysts that we use, right? Whether those are sort of molecular catalysts, they're sort of more traditional heterogeneous catalysts like you would see in the fuel cell or the electrolyzer industry, or in my case, if they're biocatalysts. It's a bit challenging if, you know, Phil makes a huge advancement on the molecular electrocatalyst side of things. Sometimes those don't apply to bioelectrocatalysis at all. So there's challenges there as we sort of look at different platforms. Some things do. So for instance, we've been talking about mediated systems. Mediators, whether you're working with mediators for a molecular catalyst, you're working for mediators in a bioelectrocatalysis situation, you know, I can use lessons that Phil learns about mediators to apply directly to my system. So, so sometimes they are direct correlations, and sometimes they're not direct correlations.
Yeah, I got to go back to Phil's comment. This is a question that I get asked often, and I view it as an organic chemistry question. And you can't turn on an electrode and stop being a chemist. It's really important that you keep thinking about things like that. You know, we have examples where we can take a sugar to make C-glycosides, and we've got methyl protecting groups on the sugar, and you have to use lithium perchlorate as an electrolyte. If you put a benzyl protecting group on it, you have to use tetramethylmonium tosylate. That initially sounds confusing, but not if you actually think about the fact that lithium perchlorate gives you a very hydrophilic double layer, and the hydrophobic molecule doesn't go into it well. And so you just tune it by making a more hydrophobic double layer. And so there are lots of things that have you take a look at a table, for example, and you see people publish a table on any method, and you take a look at, well, these are optimized conditions, but were they optimized for that substrate? And how do I think about my substrate and how I'm going to optimize it? Well, I'm going to take into consideration all the things about that molecule. And electrochemistry is no different than any other synthetic method that way. You have to adapt it to your substrate because your substrate has unique features in it.
I agree. I think, yeah, so having some sort of a fundamental understanding of the mechanism, let's say of the reaction that Phil develops, is going to help us, you know, to adopt it, either the same methodology or similar sort of concepts into new transformations. So just to add on to what Kevin said.
Okay, great. I'm actually wondering, I'm sure you all know Hector Brunia is on the call, as well as Doug Call, who is on the call. And I think George Crabtree is in here as well, who is my boss. I'm wondering if, you know, do you guys all have any thoughts on what's been talked about so far? Or maybe there's some questions y'all might have for our panelists too?
Can you hear me?
Yes.
Hi.
If you don't.
Cheers from Ithaca, yeah. From undisclosed house on 101 Thurston Avenue. I think there's an enormous potential for organic electrochemistry that's being now spearheaded by, you know, young people like Song or this whole new CCI. I think having collaborations is even more important here because for better or for worse reasons, I mean, electrochemists have generally an allergic reaction to anything mechanistic organic, and most organic chemists sort of react when they see any kind of circuit design. But with minimal sort of common language, I think we can achieve tremendous results in terms of taking advantage of the more sophisticated aspects of electrochemistry to the more mechanistic aspects of organic chemistry. And in that context, I think if there could be like a primer of, you know, organic electrochemistry to people like me, I'd be happy to give a primer on electrochemistry to the organic community. And I think that will sort of break down the sort of the barriers to, you know, more communications. And I think it's when you do that and people feel a certain level of comfort that really things move. I mean, I'm judging from all of the interactions that I've had in similar areas in terms of, for example, catalyst designs and catalyst characterizations, all of these operando methods like TEM and mass spectrometry and X-rays, where by collaborating with real experts, you can really go a hell of a lot further.
Yeah, any response from the panelists on Hector's comments?
I mean, I agree. I think Shelley mentioned the center, and I think Phil mentioned as well. It's a great opportunity to bring a lot of people together. Right? So people who are actually traditional organic chemists, as well as those who study, you know, electroanalytical techniques, battery research, as well as those who are computational chemists and you know, surface chemists. I think I totally agree with Tito. I think it's a really good opportunity. I think, I mean, it's not just opportunity. I think it's been demonstrated from some of the publications that Centers has put forward, how this sort of a powerful collaboration can result in some really innovative research.
And recall that the electrode is an active participant. It's not just a sink or source of electrons. I mean, you can modulate. I mean, that's what electrocatalysis works, right? Because you can actually modulate, and here's where sort of in some sense, design and engineering of what that surface looks like. I mean, there's a little bit of sense of deja vu because when I was in graduate school, before some of you were even born, there was this sort of burgeoning field of chemically modified electrodes where people were trying to do just, you know, things like that. For example, putting enantioselective materials on an electrode surface and see if you could get enantiomeric excesses. I think the field has progressed tremendously because we know how to do that better and how to characterize it better. And I think a lot of those things should be revisited. We should also not lose sight that there was a lot of very high quality work that was done by people. I mean, it was good to hear Larry Miller, people like Dennis Johnson at Iowa State. We did a lot of oxidation. There's a lot of literature that we have to, you know, basically remind ourselves that a lot of very smart people have worked on this with actually very limited, let's say, experimental techniques and did beautiful work.
Yep.
I mean, I think it's important to point out that that kind of communication can go both ways between the electrochemist and the organic chemist. So I'm an energy electrochemist by training, I guess. And yet I would say I spent a lot of time sort of early in my career using things that I learned from organic electrochemistry and applying them to the energy field, and now kind of switching around and learning things that I applied, things that we learned for the energy field and applying them to organic electrochemistry. So I think being able to get, you know, sort of good synergy in both directions turns out to be really important as we go forward.
Great. And so actually we have a couple questions now come in. Aditya, his microphone isn't working, so I'll read his question for y'all. Maybe the panelists can respond. Because electrochemistry is such a broad field, could you comment on how would you go about borrowing a technique or a catalyst from, say, a photoelectrochemist or an analytical electrochemist versus making a systematic hypothesis and choosing a technique or a catalyst?
Well, maybe I can just jump in really quick because Shelley and I did that last year. We worked on trying to replace a very old reaction called the Birch reduction. And the key insight that Shelley's team and we devised was that maybe we could learn something from the lithium-ion battery literature. So there's a large body of people in electrochemistry, obviously, that work on batteries. And so we were able to take that know-how from battery chemistry and with a hypothesis in mind, and then apply that to a reaction, which is a very, you know, unsafe reaction to do in organic chemistry, but could be made to be something pretty safe. So we try to operate with some sort of hypothesis before just sort of jumping in and texting random people, hey, can I have your catalyst? Hey, can I have your electrode? There's some hypothesis we're working on, but like all of organic chemistry, there's also a lot of trial and error. So there's a little bit of inspiration, a lot of empirical work that goes into it. But yeah, that's my quick answer.
Yeah, I'm going to build on that in terms of building on the empirical part of it, and that is keep acting like a physical chemist in many, many different ways. There can be a physical organic chemist, or it can be a physical chemist studying the surfaces. Look for the mechanistic clues. You know, one of the things that helped us be successful early on in adopting electrochemical methods was we would use CVs, but we also used an NMR. And going and digging out the minor products from a reaction and figuring out what they are and what does this mean mechanistically, and then how do I address that? Is the catalyst I'm using selective enough? Are there ways to fix a reaction to address that particular mechanistic item? It's really important. And that, I view that as kind of the classical reactive intermediate chemist. That's how I was trained. So, you know, Shelley came in from one side. I was a physical organic reactive intermediate chemist doing diradicals. And you figured things out by understanding what were the minor products and what did that mean about your reactive intermediate and the pathways that were being followed. And so I think just really doing things in depth when you're starting to look at reactions and understanding them is really important for moving forward and choosing catalysts and conditions.
I'll just add briefly, I think, you know, I think it's a combination of try and error and some rational design. You know, you have to know, as Phil mentioned, you have to know sort of the fundamental principles, right? You know what electrochemistry can do. It can give you control over the potential, can help you apply, you know, as high or as low potential as you want. And you know what these catalysts and molecules can do. You have some, you know, fundamental organic chemistry knowledge on different types of catalysts. And I think, you know, based on that rationale, you then just have to try and error and see what kind of conditions will give you the product you want. I mean, it can be completely rational because then it would just be, it'll be engineering. It wouldn't be sort of a reaction discovery. So, you know, I think an example we had is sort of speaking of sort of electrophotochemistry is the work we did in the past couple of years on finding new molecules that can enable electrophotocatalysis is to really look in the literature and see some of these radical anions. So the idea is to use electrochemistry to generate those radical anions and read into literature and see what kind of radical anions are first relatively stable and persistent, second photochemically active, right? So, and then once you have those candidate molecules, then you can try these reactions to see which one will give you the desired reaction. So that's my my brief answer to your question.
Just to, I'm briefly back. I think that my internet is going to hold for the rest of the call. I just wanted to build on that a little bit more because I wonder, you know, is there room to improve your intuition? Are there approaches that you think are needed so that, you know, there was the comment that if you know what you have to do, then it, you know, it's almost like it becomes a solved problem. But, you know, intuition can take you into a complete, you know, dead end as well if it's very wrong. So is there an understanding of how electrochemistry works at a point where you can be certain that you're securing your shot, or is there room to get better at it, and what would you need to get better at it?
I mean, I think we're so young at sort of using multiscale modeling in the organic electrochemistry world that, you know, I think there have been a lot of advances there in the sort of predictive ways within the, you know, electrocatalysis community, within the battery community, and we're just sort of very young. I think within that, with the organic electrochemistry community. The organic community has been sort of making a lot of progress there, but organic electrochemistry, it's something that we need to do, but we're pretty early in terms of saying that we could be predictive at this point.
I mean, not to belabor that point, but perhaps we should also revisit a lot of the work of Savian, which even though it's couched in, you know, brutally, you know, rigorous mathematics, the mechanistic insights are just unbelievable. And I don't think enough people read those papers. What we might need is, you know, a sort of Savian for dummies, you know, type of book where we can sort of demystify it. but I mean, it's just rigorous with an enormous amount of chemical intuition.
Mm-hmm.
I just noticed that there's questions from the students. Thomas, can you bring Erin? Because her question is intriguing, and I'd like to hear that take. So go ahead, Erin, and then we'll go to Sam.
Awesome. Can everyone hear me?
Mm-hmm.
Okay, so my question was kind of generally, where do you start in identifying reactions that are worth pursuing electrochemically? And I think it's worth to hear from both sides. So if you're an organic without an electrochemical background, or if you're an electrochemist with no organic background, what are some clues that might jump out that this reaction might work better electrochemically? And then especially, how do you make the reactions competitive, even though like the field of traditional organic chemistry is advancing so fast?
I can take a stab at it if you want. I think it's context dependent. So if you're a process chemist, for example, and you're, let's say, using stoichiometric amounts of an oxidant or a reducing agent, that's an obvious opportunity for electrochemistry to come in and sustainability to be the main reason why you do it. The other sort of nuanced answer, and the one that we try to focus on, is more when there's a value add proposition that presents a kind of forcing function that requires the use of electrochemistry because there is no other safe or viable or efficient way of doing it, or perhaps you have a reaction that can achieve the synthesis of a molecule in 2 steps instead of 10, then it becomes self-evident that this would be a useful reaction. And since most bond formations require the shuffling of an electron, electrochemistry can be used for a variety of, even redox neutral reactions can be done through electrochemistry. So for us, the driving force is utility. We want to work on a reaction where if it's invented, people are going to use it because it achieves a bond that couldn't be made otherwise, or because it achieves a bond that was previously really either environmentally unfriendly, non-sustainable, or very laborious to make the reagent to make it work. But I'm sure Song and Kevin and Shelley have other ideas.
I mean, I think for me, there are 2 different approaches, right? So you can either, so one approach is tool development. So you have a catalyst where you have a design principle, and you see what is catalyst, what kind of reactions the catalyst can catalyze, or what kind of transformations this new strategy can enable. The other sort of approach is that there's a synthetic problem. It's a really important transformation. There's no other way to do this reaction. And can you use electrochemistry or develop some other new techniques to do the reaction? And obviously these are 2 ends of the spectrum, and there's everything in between. I think both of these 2 approaches are valuable, and I think we've taken both. And from sort of a tool development approach, it's more, for me, I think, if I have a problem, let's say if there's a bond forming reaction that this pharmaceutical company can't do, and they come to you and ask you if you can do it electrochemically, I think this sort of this problem-based approach has more direct impact, or larger direct impact. So the reaction you discover is going to be immediately used by people. The tool development approach is, I guess, the direct impact is going to be a little smaller, but it does have a long-term impact in that if you discover a new catalyst or new way of doing reactions, this can have a more long-lasting effect, where in the future people might use your catalyst and discover new different transformations. So these are the 2 ends of the spectrum, and then we've taken both approaches and everything in between. Yeah, I don't know if Kevin has anything to add.
Yeah, no, I agree with everything that's being said. I view my group, and I view myself as more of a problem solver. And so we encounter problems, we take them on. Electrochemistry can provide really nice solutions to those. But we started initially wanting to annulate rings onto amino acid derivatives, and we needed to oxidize amides, and electrochemistry was the best way to do it, so we did it. That was the forcing function that Phil mentioned for us to get involved in electrochemistry. We've been involved in oxidative cyclization reactions because they're synthetically powerful tools, and we don't understand the reactive intermediates involved in them. And so electrochemistry is a great way of doing that. We got involved with microelectrode arrays because, well, to probe some of the biological sites and active sites that we are probing with the medical school, we needed a really nice tool for building molecules in an addressable format, so we could look at things real time. Now we know how to do that, and so we take a look into other problems. And Tito mentioned a great one, and that is that years ago people did modified electrochemical surfaces to try to get asymmetric induction. It didn't work very well in terms of the asymmetric induction part of things. So how do you keep a catalyst that's doing that near the surface? And the arrays had taught us how to do that. And so you move on from question to question, solving problems. And sometimes electrochemistry is the best solution for that. How do you know when electrochemistry is the best solution for that? Well, for me, that comes from, reading the literature and understanding what a tool does. But that's any tool, whether it's photochemistry or electrochemistry, or you can fill in the blank, whether it's a high pressure flow reactor, whether it's all the types of things. What does it really do well? There are lots of questions on problem solving, and I'm going to take a little detour now because it's something somebody told me when I was a student. That somebody was Peter Dervin. And he came to UC Santa Barbara and he told us, well, I'm going to talk about philosophy a little bit with the students. And he said, I moved from diradicals and physical organic chemistry into chemical biology because they weren't asking the Peter Dervin questions. And I have to admit, when he told me that, I sat in the room thinking, well, he certainly doesn't have any self-esteem issues. But the fact of the matter is, he was really helping us out in a nice way. When you think about your research career and you start thinking about, I'd like to move into this area, read about what's going on there. And all of you that are listening in, the students, you have unique backgrounds and you have unique questions and things that our community needs you to ask. And so read about the area and start asking, what are the questions that I can ask? And what's my background? And how do I bring the expertise that I've learned in the research I've done in the past to bear on this? And I think you'll see across many fields, the people that are the most successful, the people that come in with questions and pursue questions that they're really curious about and use their background to learn areas and bring those new skills to that area. I think I'll just leave it with that.
Anything, Shelley? Oh, I think did I freeze or did Shelley freeze? I froze, I think.
No, you're okay.
I think I'm here.
Oh no, I was just gonna ask you if you wanted to add anything to that.
I don't think so. I would say from my perspective, a lot of the problems that we solve are collaborators having specific chemistry that they want to do and are looking for electrode materials to do that. But obviously, my background is more on the bio side of things, and so we definitely have sort of biocatalysis questions that we want to answer and are frequently then going to our organic chemistry colleagues and kind of saying, okay, this is, we want to build a bioelectrode that does this. What would be a good sort of transformation, a good sort of scope to look at, what reactions would be, useful and interesting to the organic chemistry community.
I think that this is, in general, it's a very nuanced response, and it's, I wanted to call out the fact that very often I hear when it comes to organic electrochemistry that you use it when you want to go very extreme. You want to go really oxidizing or really reducing where your chemical agents don't get to that potential. And what I'm hearing a lot of is that there's also another dimension where electrochemistry can come in, which is that you may be able to get into transformations, even in moderate conditions that may be difficult to control otherwise. Is that a fair summary of what you were just saying? So there's a question on very much on an interface from Sam Plunkett. This is going to interface you with another field. So go ahead, Sam, ask the question.
Hey, can you guys hear me?
Yes.
Hi, so Thomas was hunting for questions, so I shot out a pretty general one, and that's just, I want to know from you guys what you think is the leading or current leading technologies, or even technologies that are emerging that you guys are intrigued in that focus around organic energy storage and conversion.
I guess, my lab uses a lot of the same sort of mediator, like tools that we used for mediators for organic energy storage. Claire was talking about redox flow batteries yesterday, and definitely sort of a lot of the tools that we're learning about for mediators in organic electrochemistry can be used for organic redox flow batteries. So I think that's an option, but I'm really have been intrigued by a lot of what's being done in the sort of organic solar cell community, because I actually think that we actually can learn a lot about sort of structural design of electrodes, but also maybe even some mediators and some charge protection molecules that are coming out of that field. So I think, you know, they're kind of opening our scope up in terms of thinking about what to be using for organic, in that case, energy conversion that we may be able to use from an electrosynthesis.
How about the other way around? You know, how easy do you see the connection of some of the things that you're doing? I mean, we've talked about organic transformations in the context of, you know, medicinal chemistry to get to very refined control of molecules. Do you have experience? I mean, Shelley, I know you do, because for obvious reasons, but interfacing what you're learning from control of organic molecules with other areas where it's not them giving you the problem, but you actually giving them a solution. Where, you know, like I said before, for example, in the example of water treatment, I had a very different perspective of selectivity this morning. How easy do you find it to then interact with other people that may be affected by some of the same problems that you're trying to address? This is more of a philosophical question.
I mean, I think Phil spoke to this a little bit, is that if you look at, if you kind of broke people up into sort of energy electronists and electrosynthetic chemists, the questions that they're asking and the concerns that they have are different. So in the sort of energy storage, energy conversion, we are all about Faradaic efficiency, and that is so critically important on the energy side of things. That's not so important on the synthesis side of things. And so I would say, you know, my biggest challenge coming into the community and working with people like Phil is that, you know, I kept asking him initially, well, what's the Faradaic efficiency? And it took me so long to kind of change my mental state that in this case, that Faradaic efficiency isn't the, you know, most critically important thing. But then you have the opposite of that. I think that happens if you're trying to go from the organic electrochemistry community to the energy community, because now you've really got to think about that Faradaic efficiency and how important that Faradaic efficiency is, and really designing your electrode not for selectivity, but for Faradaic efficiency. And so I think it becomes a mindset that you need to work on being flexible with your mindset to go back and forth. But I think it's definitely possible to go back and forth.
But you know, is the fine chemical the only avenue where organic electrochemistry really plays a role synthetically at the industrial level? I mean, is there no role for electrochemistry to come into more like bulk chemicals, you know, transformations that are, you know, epoxidations or things like that, that perhaps could be done electrochemically, where you're going to need the scales where Faradaic efficiency is going to matter? Is that not really an issue?
It is an issue, and I think to some extent, I'm excited in the future to look at some of those, because if you think about those situations, you care about selectivity and you care about Faradaic efficiency. So from the sort of big challenges from a chemistry perspective, I think some of those could be quite exciting from sort of thinking about electrode design perspective, thinking about the materials electrochemistry, because now you actually have to be able to do both. So you have to have that selectivity, but you also have to have the Faradaic efficiency. So it lends itself to some much bigger challenges, so to speak. Maybe longer time to having sort of practical electrodes that you could use in those environments, but definitely things that that would be, from the fundamental electrochemistry perspective, great challenge.
Let's also remember that the father of organic electrochemistry, Manny Bezier, made his name with electrohydrodimerization at Monsanto, and this was done by the gazillion tons. So there are applications for that.
And it's still used that way?
I don't know, because Monsanto is not around anymore, but yeah.
No, it was commercialized by Monsanto to about 300,000 metric tons per year. It's still being done at about 90,000 metric tons per year in a company in Florida. But there are chemical competitors, but that's not the largest process that's going on now.
But it's big.
It's big, but there, as Phil mentioned in his talk, the industrial side of things was far advanced over the application to this mid-scale range of things with respect to pharmaceuticals. So commodity chemicals, electrochemistry has a pretty strong hold in.
Oh, I see. So yeah, so it's basically the gap was in the fine control of, you know, to put the things where exactly where you want them rather than the more bulk chemicals. Okay. You know, one other thing that I don't know if it, you know, I was missing for a few minutes, but I wanted to put on the table because, you know, we were talking about intuition when I was able to come back, and I had a note on, you know, different strategies that have been coming up that you use in organic electrochemistry. And you talked about, you know, the classical of tailoring the electrode material, but you also talked about functionalizing the surface to induce selectivity, you know, the using electrolytes to induce selectivity, using electrocatalysts, using mediators. These are all different things. These are all different parameter spaces. Is it well established, you know, how you go about doing a decision tree of which way you have to go, or, you know, again, going back to the question of intuition, right?
Well, I mean, that accounts that we wrote was pretty much that. It's if you want to download that, it's a quick read. But if one knows nothing about synthetic organic electrochemistry, you very quickly, you know, find that flow chart, that tree, and know when you need a mediator, when you don't, what kind of process you should be using. So it's not just sort of a black box anymore. There's some place to start.
Would you like that place to go somewhere else, or do you have what you need? I guess, you know, we had a panel yesterday on the interfaces between computational studies to predict things and experiments. And so I wonder, in the context of, you know, pathway discovery, is there help that you could use to go faster, you know, to say, okay, I am going to use this exact route? Or is that just not possible? It's too many parameters.
I don't think it's a parameter space problem. I think it's a problem with what's the problem. And, you know, if I'm looking at a oxidation reaction and I need it to be selective based on potential, then I know I'm going to personally use a direct electrolysis to go after that. If I'm selecting based on some chemical parameter in the molecule, sterics, for example, I'm going to use a mediator that will select based on that. It's really just a matter of knowing what the tools do. And I think that, you know, in Phil's paper with this flow chart, what's really helpful is that it starts showing people, you know, these are what the tools do. And so if you have a sample molecule, you can go through and start finding the tool that applies to that. But it's the problem itself that you're tackling that's going to dictate how you approach it. But that's true of any reaction. So there is a chemical intuition that goes into doing organic electrochemistry and selecting the method.
I guess in some sense, you know, there's a number of people in the audience that are, you know, electrochemistry is very dominated by the energy storage field these days, I could see how that tree could be used in reverse when you have an organic molecule that you want to do a function in a different device, and it's, you know, it's breaking down on you. You could, I guess, use the reverse and say, okay, well, why is it, you know, what do I do to avoid that breakdown from happening? You know, I have this reaction that is happening. How do I shut it down? I assume that you could go to that tree and just run it in reverse and get to an answer. Is that fair? Or it doesn't only work the way where you want to get the reaction to go? You can't. It's not as good to avoid reactions.
Well, in some ways, there's a different problem, right? In the energy storage thing, when I look at it, I'm looking at stability of a, if I'm thinking about, I can make radical cations, I can use them as mediators. I start looking for energy storage for the most stable one. In a chemical reaction, I don't look for the most stable one. I remember when I was young, I postdoc for Barry Trost, he would tell me that, if you can isolate this organometallic species, don't bring it to me, I don't care. Because I want something that's more reactive than that. We want to do catalytic behavior. We want it to do things. And so, I take a look at the dichotomy between I want to make things that are great for energy storage in a flow battery, and I take a look at, well, what's going to transfer an electron as fast as possible. I think that there may be mixing space that doesn't mix as easily. So I'm more of the lines of, I'm an organic chemist. If you want me to work on a flow battery, I can start designing radical cations for that and can use synthesis to try to help that. I don't know if I'm going to try to find the one radical cation that fits all the jobs.
Yeah, I was thinking more, not so much in the context of using organic molecules as energy storage devices, but a more vexing question in the battery space that it appears in the non-aqueous electrochemistry space is when you have a non-aqueous electrolyte that then it's starting to do things that you don't want them to do. And so it starts, instead of passing electrons to the thing that you want to pass, you're passing them to the organic molecule that is supposedly helping you do the reaction because it's delivering. And so that's been a bit of a vexing problem in terms of how to avoid organic molecules doing things on your electrode surface that you don't want them to do. More than selecting which organic molecule is going to react, is select which organic molecule is not going to react. So that's why I was going with the reverse problem, right? You're trying to shut down a reaction rather than incentivizing a reaction.
I think
go ahead.
Just to answer your last direct question, I think there are a couple of different approaches, right? So one is just based on organic intuition. So the entirely organic chemist approach, where you can, if you have a catalyst that's reacting in a way that you don't want it, you can modify it, right? By introducing substituents, by changing the electronic structure of the molecule. What you could also do is to use, you can use cyclovoltammetry to study the electrochemical properties of the molecules you're trying to oxidize as well as your catalyst. And you can get a sense of how by tuning the catalyst, you can maybe access the potential you actually want to access. So those are some of the approaches we would take. There's a selectivity issue.
Yeah, part of the problem, and that's going to be the last thing that I'm going to put on the table before one final question on education. In electrochemistry, as I've perceived it, is that very often you're looking at processes that are happening in a very small portion of your reaction, and when your reactor, and when you're trying to do, you draw what mechanism you have, it becomes very difficult to actually observe it because it's a very small portion of your reactor, right? Is this something that matters in terms of what you're trying to do with the synthesis, or are the kinds of reactions that you're trying to do sufficiently well known, perhaps not electrochemically, but at an arrow pushing level, again, to use a crude metric, that you're pretty sure what's going on and you don't really need to exactly know what your system is doing because you already get the product that you want. So that tells you that the mechanism that you expected is valid. Is there an issue there that would help you, or not so much of an issue in your area?
I think that's why in situ and operando techniques are going to be so important to us, because we actually, do need to look at what's happening at the interface and not just do product analysis. And that means that, we have to think about DEMS or in situ Raman or in situ IR to be able to kind of interrogate those interfaces more. And certain things, there's a lot of, X-ray techniques, et cetera, that haven't been applied to organic electrochemistry at all yet. So I think we've got a lot of room there in terms of interrogating the interface that is just open for people to start to explore.
Okay, so we have 5 minutes left in the 90 minutes, and I was interrupted, but the panel wasn't, so I'm gonna respect that 90 minutes. But every panel has been asked a question about education, and is Michael there? I think he may have.
I'm here.
He's there. Okay, you're still there. Okay, I didn't see you in the chat list, so I thought you were dropped. So Mike has been asking the same question to all the panelists about electrochemical education, and your field is extremely interdisciplinary in the sense that, organic and electrochemistry, a lot of people don't see them interacting. So I wanted him to ask the question as well and get your perspective. Go ahead.
Sure. So, I mean, broadly, my question is, how do you improve teaching of electrochemistry, given that it's such an interdisciplinary field with all these different applications and different approaches? The question I've been kind of posing is, should we be having this course sort of interwoven between all these different departments, or should we have a department of electrochemistry? And on other things that other panels have brought up is whether or not we need a new textbook that maybe incorporates some of these new research applications. And so I guess I'm just curious to hear your thoughts on those, or how else you might go about improving electrochemistry education.
I would add very quickly, also you can, another angle that you could think about it is, do organic chemistry textbooks for electrochemistry well enough also? That would be kind of the flip side of that. What do you think?
So I personally think it's not just the textbook that becomes the problem. It's the fact that students will go through their entire career and never do electrochemistry in the lab. So the practical component there, depending on where you go to school, you may never be, cyclic voltammetry. You may never, see any electrochemistry outside of, maybe something that you do with redox reactions and general chemistry. And so I think, to me, that's a huge missing part. At Utah, Henry White and I jointly teach electrochemistry, and the first half of it is, Bard and Faulkner, as unreadable or as difficult to read as it is for so many students, is Henry kind of approaching transport kinetics, thermodynamics, the double layer, etc. But then really getting them into the lab with me the second half, and teaching them how to do a voltammetric experiment, teaching them how to set it up, and then of course once they get the data, teaching them to look at mechanism and do simulations, and be able to to get the information that they need to get out of that. But for most of those students, unless they came from an undergrad research lab where they did electrochemistry, that's the first time that they're doing voltammetry. And so I think that we have this sort of problem within our curriculum, that it's really hard to read Bard and Faulkner, and if you've never done an electrochemistry experiment, even figure out what they're talking about. And so you really need that practical part of electrochemistry in order to be able to really make Bard and Faulkner make sense. Because those of us who've used Bard and Faulkner for years, exactly what you need is, but that sort of relationship between all of these equations that are in Bard and Faulkner and the practical experiment that you do is kind of missing because you don't have that educational experience.
Yeah, I'm going to jump in there and say I believe we need to start people much earlier. And that the practical example of running a CV when you're in freshman chemistry and talking about oxidation potentials, and then doing an electrolysis in the organic chemistry lab, is really important for setting the stage. And I'll just make a comparison. We used to make this mistake all the time on NMR. When I was young, you started your NMR, they took an NMR class, and the first day they taught you the block equations, and you looked at this thing going, what in the world is all of this? And it wasn't until a long time after that you actually ran an NMR, you went, oh, this is actually useful. I'm supposed to go and learn this, and then you would go back. So starting people in freshman chemistry with an electrochemistry experience, and then having them run reactions in organic chemistry, and then maybe in an advanced organic chemistry with their labs, will set up that electrochemistry course to be much, much more helpful. So I believe in starting them early.
I think we need to have, and something I'm trying to do here is in sophomore organic chemistry to teach a lecture or two on electroorganic chemistry. I mean, it's a very old topic, and something that sophomore organic or sophomore graduate undergrads should be able to easily understand. You know, things like adiponitrile synthesis. Obviously, it's very relevant to real life, but also tempo alcohol oxidation. You can teach that together with chromium catalyzed or promoted alcohol oxidation. They have very similar mechanism, but very different ways of turning over the catalyst, where one doesn't have a catalyst. So I think really trying to, in addition to the experimental part, but also try and incorporate just bits and pieces of electroorganic chemistry into sophomore organic chemistry courses would definitely be very helpful.
Yeah,
so
we've used a similar approach to teach the Curtin-Hammett principle in advanced organic.
So is that, do you see that as a growing trend where electrochemistry is pervading more into organic, or is it just you guys because you're working on it very deeply? Is the field recognizing that this needs to be done, or is it still very much the old approach of teaching organic chemistry?
I mean, I think the field started to realize that, especially given how many people are working on electrosynthesis these days. I think some of my undergrads tell me that they never have taken the only thing they've learned about electrochemistry is cyclical chemistry, which is like a 5 minute of their Gen Chem class, right, per semester. So I mean, there's definitely a lot of needs when they come in my lab and they're like, oh, we don't know anything about electrochemistry. So I mean, I don't know about what other people do, but I try to, my colleague Hector Abrune is here, and he teaches a very sort of high level electrochemistry course, which is, I mean, it's a really awesome course, but I try to sit in the course, sometimes they go over my head. So I try to bridge that, bridge fundamental organic chemistry and high level electrochemistry, and try and teach a little bit of electrochemistry in my organic chemistry course as well. So that's definitely something I know. I mean, obviously Kevin does it. I think many other people are trying to do as well.
But to answer your question, nationally, I would say that sophomore organic chemistry is not the most responsive group in terms of making changes rapidly to curriculum.
I think that applies to all the chemistries, right? I've been fighting at UIC to get more electrochemistry in the undergrad curriculum because, I hear what Shelley is saying, and seeing how vibrant a field there is in organic chemistry, perhaps, now that it's so prominent for organic chemists, maybe that's when it finally will happen, because, organic chemistry is such a big component of undergraduate chemistry, especially at UIC for people that go to grad school, the medical school, right? So normally they're the biggest courses, so they have a very big driving force in terms of changes of curriculum.
And I think we want to recognize the relationship with the bioelectrochemistry community as well, and that there's so many electron transfer reactions that occur in biological systems that you can carry it forward into the biochemistry, or even if our organic chemistry classes have chemical biology now in the second semester, so you can even introduce electrochemistry into the chemical biology parts of things. So I think there are ways to incorporate it, and I think it should be much more consistent. It's almost like computation. It's better to have students start computations early and then just have it as a tool that develops, as opposed to try to hand it to them at the end of college.
All right, so we are officially over time by 4 minutes. And so I'm gonna close it on that. It's been great because every panel has closed with this question, and each panel has given a slightly different answer, interestingly enough. Yesterday, there was a lot of saying where we need to, we need a new Barth and Faulkner. And today was a lot more nuanced in terms of, what the current textbook, and it was a lot more practical in terms of the issues. Thank you, Shelley, Kevin, Song, and Phil, in the order that I see in my screen, for sparing your time to have this discussion. It was really productive, and I can tell you I personally learned a huge deal because this was a field that was very unknown to me. So I'm very happy that we could run this panel in the context of this event. Thank you all the attendees for hanging on. Apologies for dropping during the call. And thank you to all the people that are watching in the live cast on YouTube. A reminder that this will go permanently on YouTube in the recorded version shortly, and we'll make announcements once that is. Thank you, everybody. And this is the end of NGenE for this year. I'll be in touch with some of you for future editions. Thank you very much.
Thanks very much.
Thank you.
Thanks, everyone.
Bye.
Bye-bye.